All right, everybody. Hey, welcome. And I thought I'd make the solutions for exam one. I thought it would be good for you to see them and work through them depending on what you felt uncomfortable with and what you felt like you could improve upon. As I said, I'm grading the tests right now. I've done all of number one and all of number two, and I thought I'd take a moment to make some solutions here. But can't really write on your test and pass it back to you under this kind of remote setting. So I thought this would be the answer to that question of, okay, how can you kind of see that? So let me run through here. I printed up the test here. Here it says problem number one. It's got two parts, A and B. It says two protons are 1 millimeter apart. They're moving towards each other. Both are moving together with a speed of 13 meters per second. Kind of a key phrase here, after a long period of time, what is the speed of each proton? So what I would say the physics part of it here of number 1A is to realize that we have a positive, and they are moving towards each other. And so as they move towards each other, they're going to repel, and eventually they're going to kind of stop, but they're going to push off of each other and start zipping away. And after a long period of time, they would be really far apart. And that's the key. So really far apart, moving fast, that's kind of what we're thinking about here. Not a short amount of time where they just, come together and stop, but a long amount of time where they're now spread out. And also, hopefully, the other thing that clicks in when you read that about their speed, that's an energy question. That's a potential question on what we've been doing. And so this is right out of chapter 25. And we had this, that the change in the kinetic energy is equal to the change, or the negative of the change in the electrical change in energy. And that, I'll put the negative, is Q times the change in the potential. So let's start there. Let's start with the change in the potential. This was kind of what I was trying to get across in the lecture material, that this other stuff is all mechanics. The big stuff is right here is the potential. And then, of course, once that, you get the potential energy, and once that, you get the kinetic energy. And so the new stuff is about potential. And since these are only point charges, they're pretty straightforward in their calculation. So the potential is K. Why don't we say, let's look at the potential of this one here, number 2. So it is the potential created by number 1 over its final position minus K times charge number 1 on its initial position. Okay, so going to this long period of time, we know that this number, I'll just put infinity here, is the final potential energy. So basically the final is 0. And then this is Coulomb's constant times the Q number 1, and its separation is that, what I read here, 1 millimeter. Okay, so this would be 0 final potential, and the beginning potential would be 9 times 10 to the 9th. For Coulomb's constant, the charge would be 1.602 times 10 to the minus 19, and their initial separation is the 1 millimeter. So grabbing my calculator, 9 times 10 to the 9th, times 1.602 times 10 to the negative 19 divided by 1 millimeter gives me a change of, and it's a decrease, there's the negative sign, and what was this number, 1.44 times 10 to the negative 6. So that would be the change in potential, of course measured in volts. So then if we take what we mentioned earlier, which would be the change in kinetic energy, let me write it as 1/2 m v final squared minus 1/2 m v initial squared. And let me point out that if I let m and v be the motion of one of them, then the other one's doing the same thing. So let me make sure I double that for the change in the kinetic energy of total, because that has to equal then to the change in the potential energy total. So it's easy to overlook perhaps that there's two objects here. And then, of course, I have this negative, and the charge then, number 2 would go here. So this is this 1.602 times 10 to the negative 19. And then the change in potential is this negative 1.44 times 10 to the negative 6 volts that we got earlier. And if maybe I'll just distribute this 2 a little bit and factor out an m and put in the initial speed of 13, okay. Maybe I should even point out m is a proton, which is the 1.67 times 10 to the negative 27. And then this number, if I go ahead and keep multiplying, times 1.602 times 10 to the negative 19, comes up with 2.31 times 10 to the negative 25 joules of energy. So the change in energy is this much, and it all goes to the kinetic energy here. So if I take that and then, of course, divide it by the 1.67 times 10 to the negative 27 for the mass, I get this number. And then, of course, when I move that 13 squared to the other side, it becomes a plus 13 squared. And then finally, if I take the square roots of all of that, I get a 17.5 meters per second. So there would be the answer to 1B using conservation of energy. These protons will come in, push off each other, slow down, ricochet, I guess is a good word, ricochet off and goes back. And so after a long period of time, when they got really, really far apart, as we calculated infinite distance apart, or at least far enough that it's essentially infinite, we would be going 17.5 meters per second. Let me tear this off and then go to 1B. Hopefully you kind of see the same logic in 1B. We got a different configuration, so a little bit harder, although they're not moving, so that makes it a little easier. But it says we've got the 3 stationary protons are held into place in this equilibrium triangle with, again, sides of 1 millimeter. And, of course, my hint for you is that you can save yourself a little bit of time. I tried to have you be focusing on the physics, not on a bunch of computations here. And so if I start here kind of with that same logic that we did in part A and say, okay, I've got these 3 protons, and they're going to push off each other, and they're going to be moving outward. And so, again, after a long period of time, they're going to be really, 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 really far apart. And so, again, I can say the change in kinetic energy is negative the change in the potential. And if I go ahead and just apply the change in potential to all 3 of them, I learned back in number 1 that a group of 2 of them had this much energy right here, 2.31 times 10 to the minus 25. So if you wanted to know what the change in potential of this whole group, I guess you would start off by saying, well, final minus initial, and the final, they're going to be really, really, really far apart. And so we can kind of use this idea that when they're really, really far apart, they have no energy. So this would be a minus, then here a 0 minus. And this is where we can save ourselves a little bit of work, and we got to be a little careful counting it. We know that 2 protons that are separated by this distance of 1 millimeter have this much energy. And so you kind of think about how much energy would it take to kind of assemble these. You might say, okay, I'll bring in the first proton. Well, that took no energy because there was nothing repelling it. But when I did the second one, let me put the second one right there, that would be this much energy. Then when you bring in the third one, there would be an energy associated between those two and those two. So really, it's how many energies associations do we have? You might say, how many bonds do we have? And we have 3 of them. And so that would tell me that each bond, each connection is this much energy, and I have 3 of them. So this would be 3 times the 2.31 times 10 to the minus 25 joules. And so that's how you might save yourself a little bit of time. And so if I go 3 times 2.31, I get 6.93, and of course still times 10 to the minus 25 joules. So that's the total energy I get from all 3 of them. And then of course over here there would be this 1/2 mv final squared minus 1/2 mv initial squared, and that would, if we think about that as the change in kinetic energy of one of them, the symmetry here tells them they're all doing the same thing. So multiply that by 3 to be the change in energy of the whole system, if you will, all 3 of them. And so I can factor out the 1/2 and the m and put a final squared and recognize that the easier part of this b is that they have no initial speed. So if I take this 6.93 times 10 to the negative 25 and multiply it by 2/3 from here, and then divide that by 1.67 times 10 to the negative 27, I would get just my v squared. And so if I took the square roots of that, I would get 16.6 meters per second. So that's the thinking and the idea behind number 1, that it's right out of chapter 25. It has to do with the potential and the conservation of energy and how that's related to the motion of some objects, and starting easy with 2 objects and going to a harder one with 3 objects. That hopefully isn't hard to calculate because of the way the numbers are laid out. So I tried to do that a couple times. You'll see that again in number 3. Okay, because these can be long problems, as you no doubt learned during the homework. So trying to make a test that would test your physics but not bog you down in too much time and calculations. All right, so let's look at number 2. Number 2 here. And the first one, 2A, is exactly number 25 out of, or no, 29? I think it's 29 out of chapter 23, where you were asked to get no, sorry, getting ahead of myself. It's still right out of the homework or right out of the book. Sorry, it's an example in the book, and it's Gauss's law, so it's out of chapter 24. But it says for a very long rod of radius A, if the rod has a uniform charge density of a lambda, use Gauss's law to find the electric field outside. Well, given that this was open book, hopefully, and not just that it was open book, but also that we did it in the lecture, you did it on the homework, it was done in the book, that you nailed this one. Because this one, you could, being an open book, you could just go right to the example that worked this out. So I would, if I was working it out without the book, just say, okay, put a Gaussian surface around it. Maybe make the Gaussian surface of length L and of radius R. And so when I do this dot product and the E dot dA cosine of theta, we could argue that you can pull the electric field out. We could argue that the angle would be 0 degrees and that the area of a cylinder, the surface area of a cylinder, would be the circumference 2 pi r times the length. I guess that's worth showing you again with a little sticky. You know, if this Post-it note, you wanted to know the area of it, its surface area, you'd go its length times width. But if it was, you know, rolled up in a cylinder, you would have the length, there's the L, and the width would be the circumference, the 2 pi r. So that's the left-hand side of this equation. And the right-hand side of the equation, of course, because it's uniform, would just be its charge density times its length. In fact, that's probably worth pointing out. I mentioned it a few times in the lecture, but it only works that way if you have a uniform charge density. And that's going to change in part B, because remember, charge would be an integral of dq. And if you are then saying lambda is a dq over a dx, you could replace dq with lambda dx, and then you could pull out the lambda and just have an integral dx, which would be the integral, that would be the length of your Gaussian surface, and you get your lambda L. But notice that only works right there in this magical step that you can pull it out. So hopefully you notice that, because you're going to run into troubles if you just blindly copy that from the book. You'll get part A right, but you'll get stuck on part B. So continuing on here, this is just lambda L over epsilon naught, and the L's cancel off, and we can simplify this to 1 over 2 pi epsilon naught, lambda over r, kind of the way your book did. Actually, I think your book actually then replaced the 2 pi epsilon with 2 over Coulomb's constant. And either one of those, of course, is the same, and so therefore right. And so that's part A. And so like I said, and I've already graded this one, and yeah, most of you just nailed that one. But hopefully you were understanding it and not just copying what was in the book, because then part B will kind of test you on that. Did you really get this idea? And so doing the same kind of logic here, drawing a Gaussian surface, maybe I'll do that in red, drawing a Gaussian surface on the outside and calling it L and calling it radius R. The starting point would be the same. You would write out Gauss's law, E dot dA is equal to the charge inside of the Gaussian surface over epsilon. And the left-hand side would actually come out to be the same for the same logic. You would take the dot product, like we did up here in A. You would argue that the electric field is constant over that Gaussian surface, whatever it is, that's what we're trying to find. You would argue from charge symmetry that the angle would be 0, and so you would get this dA. Of course, you need to be careful about what area, and I'll come back to my little Post-it note. This is the Gaussian surface I'm creating, and it's along the surface that is rolled up. This is the part that's sticking out. The top part of the Gaussian surface, the flux just goes radially outward. So these have 0 and 0. So technically you might say that this integral actually has 3 parts, because there's 3 surfaces. There's the top of the Gaussian surface, the bottom, and then what I call the face of the cylinder. And so we really only care about the face, because the top and the bottom, the dot product is 0. It's an angle of 90 degrees. So that's why I'll just kind of skip over that, like at least in the solutions here. I did the solutions in class and really argued this point that you can't ignore it, but it's 0. And so in this case, I'll just say top and bottom are, 0, because of the angle would be 90 degrees. But the face part is 0 degrees, and so we're talking about the area of the face. And I probably should have mentioned that all back back here. So there should not be a pi r squared or anything. We're not talking about the area of the top or the bottom. We're talking about what happens on the face. And you can see when you unroll it, that length, well, that would be the length, and that would be the width, and that's the 2 pi r. So there's the width, and there's the length, and that's how you get the area of that Post-it note. Now, what makes this problem hard is really over here in B. So I'm just going to put my epsilon naught alone and then write this, as I started to mention over here, that to get the charge inside, you really got to add up all the charges that is inside this Gaussian surface. And then that's where the density comes into play. Density is the charge divided by the volume. So maybe the first step is to replace then the dq with rho dv. And of course, now we're going to be adding up the density in the volume that is contained within this red Gaussian surface. And again, this is where my comments about part A are real important. You can't just pull the rho out in front of the integral and get rho v. That would only work if rho is a constant, and you can see it's an equation, so cross that out. But at least we could put in the value of the equation, and so it's E minus alpha r. And so that's what's given here for the equation for the density. So it's a decaying exponential. If you wanted to draw a graph, I suppose you could. It would have a value of 1, and as you moved off from the center, it would go down if you kind of wanted to understand. So this charged rod then has a lot of, most of its charge packed in the very center of it and decays away as you go to the edges. So that's the density. And then you've got to do a volume addition. And if you think of these as concentric cylinders, and so I'm going to add up maybe what I'll call a little shell, and wrapped around that another little shell, and wrapped around that another little shell. And so cylindrical shells are being added up. And so the question would be something like this: what is the volume of this shell that you're adding up? And I think maybe it's a little easier to see it again with a little Post-it notes. And so maybe I'll roll this up again here, and this will be my shell. And so now this time it's representing the shell. It's not representing the Gaussian surface. But what would be the volume of this shell? And again, I think you can see it better once you unroll it. You would say it's its length times its width times its thickness. So in this case, its length would still be the L. Its width would be 2 pi r. And its thickness would be where our calculus comes into play. It's, how thick this is. It's a dr, and we're going to add up a bunch of drs. And coming back to the picture, then, we can also say, then, well, we're going to add them up from r equaling 0. Okay, so there's my r equals 0, until I get to the edge of my charged rod here. So I won't go all the way to little r. What I will do is add up to just to A, because that's where I get to the end of my charges. And so I need to stop at A to see how many charges are in there. Okay, so then I'm back to math here. Maybe I'll write my E, my 2 pi r L on this side, because I can see that there is an L and a 2 pi that I can pull forward out of the integral, and I'll be left with an integral from 0 to a of e to the minus alpha r dr. And the 2 pi and the L show up on both sides. So bringing the R over here, that's going to be the part that is the functional form. And then this, whatever this integral comes out to be, is going to be my answer. Now, this is where I said, okay, save yourself some time and don't try to integrate this. Go right to the integral tables, or you could integrate them. I think I actually didn't even try this one. I think it's an integration by parts, so it's not an unreasonable one. But I'm just going to grab the textbook here and go to Appendix B here. I don't know if I can find Appendix B, and I know it's near the end. Here it is. And so the one we're looking at then looks like this one here. And so there's an x and an e to the ax dx. And of course I got to compare it with what I got. And so I guess I need to be careful here. So and there's everywhere that I see an r would be their x. Okay, so we'll replace r with x. And everywhere they have an a, I would have a negative alpha. All right, so that means I would have e to the minus alpha r, that would be here, over a negative alpha squared, okay, and then a negative alpha for that a, an r, and a minus 1, all evaluated from 0 to a. And it could very easily confuse this a in our problem with this a in that integral. So be careful. That's an alpha and that's an a. And I've seen a few of those mistakes as I was grading them. Just like, obviously that could be easy to do. But don't confuse alpha with the a. And the a is going to go in place of the r, not the alpha. So, I'm going to have a lot of alphas left over. And then a's and alphas when I'm all done with this. Okay, so I'll put this back here and say, okay, let's keep going with this integration. I'm gonna need another page for that. Bring that page I'm working on here. And so this will say E equals, and so I've got 1 over my R epsilon naught, and maybe I'll just make the alpha squared here. And now I got to put in my A. So this would be E to the minus alpha A minus alpha A minus 1. And then the other part of the limit is at 0. Okay, so put in 0. This would be e to the 0. This would be 0 minus 1. And so 1 over, there's the r, there's the epsilon, there's the alpha squared. And I'll jump over to here because 0 minus 1 is minus 1. E to the 0 is 1 and another minus, so that just makes a plus 1. And then I've got these two that are negative. I'll factor that out and get 1 plus alpha a, and I then have e to the minus alpha a. Yay! And so there is what I get after I integrate and say, okay, what is the electric field outside? So it's a function of r somewhere. Of course, it depends on alpha. And, of course, does depend on the A, the radius of the disk, because that's how much charge is inside there. But it drops away as a 1 over r squared value. So that's not a surprise that it drops away as a 1 over r squared value. All this other stuff then must be, the charge inside based upon what we just did on that integral. So that's a bit of a challenging one for sure. But like I said back here at the beginning, hopefully you just nailed the first part really well, because you could just kind of copy it out of the book. But don't blindly copy it. Understand what you did, so you could do this one here that's a little different than something that's directly in the book. All right, well, with that in mind, I'll move on to let me put this away. Let's see, where are we? Number 3. So, bringing the test over here. Here is 3A, saying, all right, find the electric field at this point. It's along the perpendicular bisector. This is the one that I started to mention in step 2. Got ahead of myself. But this one, again, right out of the problem set, I believe was number 29 on chapter 23. Could have been 25 in chapter 23, but it's definitely a Coulomb's law. And again, because it was open book, hopefully you could go right back to your homework and say, okay, what did I do? And nail this one. I haven't got a chance to grade it, so I'm trusting you nailed that one. And if you did, then hopefully you nailed this one. That's not directly in the book, but it's an extension of that one. And actually, very simple. I hope I'm real curious if you caught how simple this one really is here. But let's start with this harder one. Although, like I said, since you've done it in the book, hopefully it won't come across as hard. So let's say here is A, and it would look something like this. If you have this long rod here and you come along the perpendicular bisector to some point, let's call it Y, and you might as well make a grid and call this distance here X, and you take a little bit of chunk of charge right here, dq, you'll realize then that this would make a little bit of an electric field pointing off in this direction. And one of the things I kept emphasizing in 23, and let me do that again, is that look for symmetry. You can save yourself a lot of work, and they're asking for the electric field, and hopefully the first thing you notice is that the electric field in the x direction is 0. You're already halfway done with this problem, because there are these symmetric or symmetric twins was the phrase I like to use, and this electric field would have an up component and then a horizontal component, and also an up component, vertical, and also a horizontal. But the horizontals are equal and opposite. The angle's the same, the charges are the same, the distances are the same for this little symmetric twin charge compared to that one. So in the horizontal direction, you will have stuff pointing left, but you will also have an equal amount of stuff pointing right. And when you add all those together, you're going to get 0. And so that's a big and hopefully very useful step that will, like I said, you would see that, right away. You would be done with the x component in hopefully about 3 or 4 seconds. And of course, you wouldn't be talking like I am, so hopefully it wouldn't even take you the 30 seconds it tells me to try to explain this. It's just a 0, and then you're going to move on to say, okay, now let's look at the y component. In the y component, we would add up all those little y components. And they don't cancel off, but maybe you could do some kind of argument along this line. Maybe you would say that, okay, well, they don't cancel, they add together. So that is if I add up all the charges from 0 to half the length of the rod, so calling L the length of the rod, then whatever I get, I just double it because I'd get exactly the same thing from the other half. So yeah, that's kind of this logic in here that you would use the symmetry to quickly hopefully say x component is 0 and the y component is twice what you would get if you just added up from the center out to one edge. So that's where I have. Now our Coulomb's law comes into play here, because this would be then the magnitude of the electric field times cosine of an angle. That is, if we were to call this angle here theta, then the y component here is the piece that is adjacent to the magnitude. So if that's the magnitude, then you multiply by cosine theta to get the y component. And so that's that big component step. You're working with vectors, kind of the thing you learned in 121 last semester or the semester before, or wherever you had the 121. And of course, all throughout the homework in chapter 23 here was all these vectors, and 24 too. Now in 25 we got away from vectors. That was good because we were doing potentials, but and not completely away from them, but since they build on it, but potential is a scalar. But this is the electric field, and it's not a scalar, and so we have to do the cosine of the angle. All right, so here's our limits. Oh, and I guess I didn't put my limits on this integral there. But this would then be Coulomb's constant times that little chunk of charge times the distance away squared times cosine of theta, if I kind of just directly input Coulomb's law into it. And then here's where we could use that little trick of charge density again. Remembering, we'll come up here, lambda is the charge per the length. And so a little bit of charge over a little bit of length then would be that dx. So I can replace this with lambda dx. So that's an important big step because, as you can see, I am thinking in my mind that I'm going to be adding up from the center of the rod out to the edge. So adding from the center of the rod out, I'm kind of thinking of dx. So at this point, and even this point here, I don't have dx's. I have a dE, which I then use Coulomb's law to change to a dq, and then I use charge density to finally change that to a dx. So I got to get to the dx before I can actually do the mathematics. So there's a couple of steps of substitution before I get to the dx. And so finally I'm there, and 0 to L over 2 is going to be the limits of my integration. And then here's the x, or the r squared, coming back over to here, doing kind of Pythagorean's theorem. As I'm adding across, calling this the x, then x squared plus y squared is this distance, which we'll call r squared. So this would be the x squared plus the y squared. And of course, the square root of that is r, so I have to square it again. So that's why there's no square root there. And then cosine, the last little piece here, I can look down below. This angle and this angle are the same. These are vertical angles. But then I would have this y over the r. And so I'm going to write cosine as y over the r. And then this time I will have to put a square root, because it's r, not r squared this time. And so it's x squared plus y squared. So then my integral looks something like this, and this is the important piece right here, the x squared plus the y squared to the 3/2 power. So 1 power there and a 1/2 power here. And then these other things are a constant, Coulomb's constant, lambda, and y, and then the dx. And so as I add up all these chunks of charges, going from my limits of 0 to L over 2, none of this stuff in the numerator changes. So I'll just pull it out in front, and I have this dx over this x squared plus y squared to the 3/2 power. And again, from 0 to L over 2. And this is one that, like I said, you did on the homework, and I think I worked it out in the lecture, and I did a solution on it, a video solution on it. But this is one that is best done by a trig sub, but not during a test. During a test, it's best done by just looking it up here. So that's my hint to you, and I'll grab the integral tables. But I think the one we're looking at is right there. There it is. It exactly matches that one. It's got the dx and it's got the x squared. Now they have an a squared instead of a y. So again, just kind of comparing mine to theirs. Everywhere they have an x, I will use an x. But everywhere they have an a, I will use a y. So looking at this, I will put an x in the numerator, and I will put a y squared in the denominator, and I will put a square root of x squared plus y squared down here in the bottom, and then evaluate that from 0 to L over 2. So there's the integration that, like I said, is a good trig substitution integration, but don't spend too much time on that. All right, well, continuing on here. Let's see. I have then, so electric fields in the y direction. And I guess I would have something that would look like this. I would have the 2, the Coulomb's constant, the lambda. And let me just cancel a y on each of those. And then let me put in the limits here. I would put an L over 2 over the square root of L over 2. So that would be L squared over 4 plus the y squared. Minus then putting in a 0, so that's just a 0. And then even this can be simplified before I kind of punch in my numbers here. I see that my 2's would cancel off. And I also kind of see it, it's buried in here, but the charge density would be the charge divided by its length. And so that length would cancel with that length. And so I would have just Coulomb's constant times the Q here. I don't even have the length in here. And then I have this y. So Coulomb constant times the charge. There's my y. And over here, I would have 1 over the square root. And then this would be the L squared. You know what? Just to make it easier when I type it in here in a moment, I should have probably left it as the L squared over 2. I'm going to go back. Because I remember they told me the length was 12, so if I just cut that in half, that's a 6. It'll be easy to type in a 6. And it'll be 0.06. All right. So now I think I'm actually ready to put in the numbers here. So grabbing my calculator and the instructions to the test, Coulomb's constant is 9 times 10 to the 9th. And the charge here is this 15 microcoulombs. And the y, you see, they say 6 centimeters from it. So it would be 0.06. So I'll just do that one first. This one's a little more involved. Maybe I'll do it by itself. It's a 1 divided by the square root. And this is what I was saying here, is the L is a 12, and if you divide it in half, that's a 6. So this would be 0.06 squared. Add to the y, which is the 0.06 squared. Okay, and so that's this other factor. So if I take that factor, that 11.78, and multiply it by that first factor I got, I get this 2.65 times 10 to the 1, 2, 3, 4, 5, 6, 7 newtons per coulomb. And so there's, like I said, the worked out answer, and plug those in. Now I'll be curious to see how many actually worked it out, or maybe just did the author's solution. But so he does the sine of the angle there in 29, and this is, if you put this L here over, see this L over 2, yeah, this together, this L over 2, back to our picture. Another way of doing this is, if you look at this big angle here, what you might call the final angle, that would be L over 2, and then we're dividing it by R, so it would be the sine of that big angle. So you could actually write this as the sine of the big angle right here, and then just have the rest of that. And I think that's how the final solution was listed on that example. But I think this is easier, given the way our problem is set up, than what 29 was set up. So a little different setup. All right, well, on to 3b then. Oh, maybe I should say this is the y direction, because the problem actually did say magnitude and the direction. And so to finish this, I guess I would say, so the electric field is 0 in the I hat, and 2.65 times 10 to the 7 newtons per coulomb in the j hat direction, or just say, you know, it's along the perpendicular bisector. So there's nothing along the direction of the rod. There's nothing along the length of the rod. It's perpendicular to the rod, and so that's the direction, and that's the magnitude. And then B is kind of an interesting one that hopefully you caught it here, that if you had like the first rod here, and maybe I'll call the one down here the second rod, and the one connecting them the third rod. And so we're kind of looking at this. Maybe I should just draw it right on here. The electric field from this top rod, number 1, would be pointing like that. And from this bottom rod would be pointing like that. And we're right in the middle, so they'd be equal and opposite. And so the field from those two is canceling off. And so what you end up getting is the field equivalent of just one rod. And that was then the same numbers. So right here, the field would be just horizontal in the negative direction. That's the result of all 3 of these rods, because top and bottom, 1 and 2 rod cancel off. Only 3 makes anything useful. So I would say the total electric field is a magnitude of 2.65 times 10 to the 7 newtons per coulomb. There it is, just one rod. And of course, the way it's set up, it would be in the negative I hat direction if we list the direction in terms of the I hats and the j hat. But you could just say horizontally to the left would work too. So that's what I meant earlier when I said B is actually a good one and also a pretty easy one. It's all really about physics, and it's not so much about a new calculation, a bunch of math, a bunch of integrals. So again, I'll be curious when I start grading this soon. And hopefully I'll get to it by this afternoon, or definitely, tomorrow. Probably not too much because of a lot of Zoom sessions tomorrow, but some grading. I should get to it. But definitely then finish things up on Saturday and Sunday. All right, but I hope you did that one well. And then the last 2 are from our practical chapter. These are about capacitors. And so we'll start here with number 4. And number 4, maybe the first thing to do is to recognize that power we learned about the equivalent circuits. And so maybe the first thing I would do here in number 4 is to recognize that the 3 and the 7 are in parallel with each other. And actually that's kind of a trick. That's what is kind of a struggle here at the beginning. And whether or not things are in series or in parallel. And these are in parallel. One way to say that is they are connected by a wire here. And a wire is a piece of metal, no electric field, so therefore it's an equipotential. And then they're connected with another wire. So my logic was if you could draw a line with nothing in between it, these plates would have the same voltage. And then these plates would have the same voltage. So the difference from one plate to another in the capacitor of 3 would be the same as the capacitor in 7. They have the same voltage. That's what we call parallel. And so this would be saying here that this circuit is the equivalent of something that looks like this. This is still the 3.9 microfarads, and this is still the 12 microfarads. But now this one being in parallel, I would add together. And so this is an equivalent circuit. In fact, I would even go one step further and say, well, wait a minute. Isn't the 12 and the 10 in series with each other? So I won't touch the 3.9, but I will go down and say that the 12 and the 10 are in series with each other. And so if we take the reciprocal of the 12 and add it to the reciprocal of the 10 and take the reciprocal of that, we should get its equivalent. So I'm grabbing my calculator, 12 reciprocal, 10 reciprocal, add it, take the reciprocal of that, and we're looking at about a 5.45 microfarad capacitor. And so maybe I'll call this the equivalent of the equivalents. So we have the original circuit, then we have the equivalent, and we have the equivalent of the equivalent. And we could, but it's not necessary, go one more step and get the equivalent of the equivalent of the equivalents. But that's actually going to make things harder, not better. Because when you realize the equivalence of that with these would be in parallel, then you are saying that these two, I mean, if you actually did draw it, it would look like this. And the advantage of that one is to say that this one capacitor has on it the full 6 volts. And I said I wasn't going to draw it, but I did. But what I wanted to convince you of then is that would tell me that these two, because they're parallel, have the same voltage. The 3.9, in other words, has the 6 volts. So way back here in my table, I could just put right here 6 volts. And so I'll just go units of volts. Yeah, 6 volts. That's what that's saying. In fact, I really didn't even have to go that far. I hope you can kind of see it right here. This one loop, this conservation of energy, would then say here that, okay, if you go around a loop like hiking a trail, you have to go up and down the same amount. I mean, if you park your car right here at the trailhead and you change by an energy, a voltage here, so on a hike, that would be like going up in altitude. And then you go over here and you go down in altitude. You've got to go up just as much as you go down when you get back to your car. And if you didn't, it would be weird. You would like be above or below your car. You would like, hey, here I am in my car, but I'm 30 feet below. I'm underground here. How do I get to my car? And conservation of energy says you got to be the same. So if going around here, this has to go up by 6 in order to here to go down by 6. So however you want to look at it. Oh, by the way, that argument I just gave was given by a guy named Kirchhoff. So we're going to have Kirchhoff's laws coming up here in chapter 28. We're about to start next week. And that's his argument, a conservation of energy argument. But that's where I get the 6 volts. So I could have seen the 6 volts way back here at the beginning, but I clearly see it once I get to the equivalent of the equivalent of the equivalents. And right here, this equivalent of these two has 6, and the equivalent of these two are these two that are in parallel, and so the 3.9 does have 6 volts. So that's kind of where I would get started. In fact, not only would I recognize that 6 volts, but remember, capacitance then is charge over the voltage. So once I know any two of these, I can then find the third. So I would just take the 3.9 and multiply by the 6. There's the capacitance, there's the voltage, and get the charge. And so this is the 23.4. And then this would be microcoulombs of charge if I wanted to know what's the, charge on that. The charge on the capacitor. Okay. So that's probably the easiest of them. And so like I said, maybe it was good I did draw that one, because that helped me realize that it would be the same voltage if I didn't recognize it already. But really, the equivalent circuit is this one, the equivalent of the equivalent, because here is kind of an interesting one, and I can do the same logic here. I know that this is 6 volts, and so if I ask myself, well, how much charge would be then on this capacitor? Well, it would be the 5.45, it's a capacitance, times the 6 volts. So if I grab my calculator here, 5.45 times the 6 comes out to be a 32.7. Now, like I tried to convey to you, and hopefully has been working, The equivalent circuits are wonderful, but only in the sense that they help you get back to what is really going on in the real circuit, because that's the whole point, is what's going on in the real circuit, not what's going on in these equivalent ones. But these equivalent ones can often be easier to understand, and I think this is an example of that. This would be saying that the charge that comes out of the battery and moves on to these capacitors, some goes on to this capacitor, which we already said would be 23.4 coulombs. And now we're saying the charge that would move on to this capacitor would be the 32.7. And if you take this circuit, the equivalent of the equivalent, and you come back to the original one, what you're saying then is that the charge would come out of here and go right onto the 12. And so what I've calculated is the charge on this equivalent one as 32.7, but coming back to the real circuit, that would tell me that that's what went on the actual 12. So this is then the 32.7. And so that's how something like the equivalent circuit, technically the equivalent of the equivalent circuit, leads me back to the real circuit and lets me conclude then how much charge is on what I really wanted to find. So there it is. That's what I really wanted to find. And let me point out again, now that I have the charge on this 12 microfarad capacitor, I could then find its voltage. And so grabbing my calculator, if I take the charge, which is already in my calculator, 32.7, and I divide it by its capacitance, that would give me then the voltage. And so this would be a 2.73. Where this, again, becomes really nice, maybe using that information back here to this one, the equivalent one. Because, again, this up here is 6 volts, and so kind of saying that the voltage change on the 12 and then the voltage change on the 10 must be the 6. Because the 6 is connected to the 2 in series. Again, conservation of energy, or my analogy of going on a hike would be to say, if I parked my car here and I would go up in voltage, I'd go up in voltage, and then I would go down back to my car. Now, I know down is 6. That's labeled 6. So that means this up and up has to be 6. So in other words, when I go up a little bit and then up a little bit more, that total has to be 6. And I just said that this first up is, I guess I wrote it here, 2.73 volts. So that tells me that the up on the 10 here would be that difference. And so 6 minus 2.73 is 3.27 volts. So that's how much must go up on this one. But watch, come back to this original. This 10 is the equivalent of these two together. They're in parallel. They have the same voltage. So these two have not only the same voltage, but they have the same of what this equivalent is. And so I just found it. I suppose in terms of discussing hikes, you could think of it this way, that if I park my car here and I go for a little hike and I go down and around, here I'm saying I go up 2.73. And so I get right here to my little hike, and I could go either way. I could go on the John Muir Trail, or I could go on the Stairway to Heaven trail, my choice. All right, which are, by the way, 2 parallel trails there in Yosemite. And it doesn't matter which one I go. And so sometimes I'll go this one and sometimes I'll go that way. But either way I go, I got to go up the same amount to get to the top of the waterfall. And so that if I already went up 2.73, I know the other path has to be 3.27. They're both 3.27. And so if I go up the John Muir Trail, I go up this amount. Spread out over a longer distance, so it's not as steep. That's why if I go this way, I got to take a staircase. That's why it's called the Stairway to Heaven. But it's a beautiful view right on the edge of a waterfall. So it's great, unless there's a lot of water, and then, well, then hopefully the rangers close it because somebody's going to die. But over here. But anyways, this then is telling me that I have a 3.2727 voltage for each of those. Okay. Now, to finish this problem, remember, if I ever have any two of these, I can find the third. And so coming back to this equation, I could say take the capacitance 3, multiply it by the voltage, 3.27, and I get a 9. And doing the same decimal places, I'll just call it a 9.8. And then over here would be 7 times 3.27. And this would be 22.9. And I'll tell you a little secret I like to do is before I say, okay, I'm done with this problem, I just kind of like to double check things like conservation of energy and conservation of charge. And I usually know if I've done it right or not, and which will tell me if I got to keep working on this. Because look at this for a moment. If as we said earlier, this charge comes out of the battery and it's 32.7 that goes on capacitor number 1, then it comes off of capacitor number 1, or the 12, and then splits between these two. So the charge on either one of these should be less than this one alone. And yep, sure enough, either one of these is less than that. And better still, the charges of these two should add up to the charges. Because remember, it came off of here and then separated. And so again, this is like a hiking trail. Especially in Yosemite, there might be, in a given hour, 100 people that go this way. And then they split. And some go this way and some go this way. And what you know is during that hour, 100 people will be the total of both paths. Each path will be less than 100. Unless it's 100 and a 0. But it's usually not. Usually there's a split. And then also that total's got to be 100. And let's check my total here. So 22 and 9 make 31, and then this makes another 1.7. So there it is, 32.7. Yeah, these two do add up to that. And so that's my conservation of charge argument. My conservation of energy, I kind of already went through, but I'll mention it again. These are in parallel, so they should have the same, and they do. That's how we got them. Also, these two should add up to 6. And so this and the 7 should add up to 6. It does. And then this and the 3 should add up to 6. And sure enough, it does. And this one by itself should just be 6. This is like a straight path, just straight up 6. Whereas this went up a little bit and then split, and you could either go that way or that way. So this plus this got to be 6, or this plus this has to be 6, or just that has to be 6. By the way, I never did say all 4 of them have to add to 6. I hope you are not still thinking that. Sometimes people, beginning students, will see this circuit and go, oh, there's 6 volts, so all of these voltages add up to 6. No. That is not at all what the voltage means. It is the increase per charge, or per individual if you're thinking of a hiking trail. And so when you put all these people on the hiking trail, the people who go this way go up 6. The people who go this way go up 6. People who go up this way go 6. So this is an increase in 6. This and this total is an increase in 6. This and this total is an increase of 6. But not all 4 of them are 6. Nobody would say, oh, that's a 6 when I go this plus this plus this plus this. I don't know how you would even do that hike. That's not what that 6 means. All right, well, anyways, there's what number 4 is. And it's the beginning of your circuits. We're going to see a lot more circuits as we get into resistors and currents now. And recognizing series, parallel, and sometimes neither. So far, we've only studied series and parallel, but circuits can be hooked up series, parallel, or neither. Series and parallel are just nice ones. But the neithers are a little harder. And we'll be talking about those, but not for this test. Okay, and then finally to the last problem, problem number 5. Number 5, again, is from our practical chapters about a capacitor. Looks like it's a 3-part here. It says a parallel plate capacitor is made with 2 square metal plates. The plates are, it looks like, a 0.5 millimeter apart. What is the length? This is A. What is the length of the square side if the capacitor is filled with air? It's connected to 2,000 volt power supply and it holds this much energy. Well, one of the things that I hope you got out of chapter 26 was that our capacitors, as they are storing this charge, store with them energy and electric fields. And so that's what this one is focusing on. And so if we were to put in the energy, which they said is the 3.54 times 10 to the minus 4, and we know we're connected to a 2,000 volt power supply, kind of this first step of A would say I could find that capacitance. So grabbing my calculator, 3.54 times 10 to the negative 4 for the energy. Multiplying that by 2 and dividing it by 2,000 squared would give me a capacitance of 1.77 times 10 to the minus 10 farads. And the other thing we learned is that for a parallel plate capacitor, it is epsilon naught, that's the permittivity of free space, times the area of the plate and the separational distance. Now in this case, since we're talking about a square, I'll just put in L squared. Permittivity of free space is the famous 8.85 times 10 to the minus 12. Hopefully you're starting to commit to memory. I'll be a little careful with the units here. That is millimeters, so the separation here is a half a millimeter, so 0.0005, and then the L squared. So I've already got the capacitance, so I'll just move this over, 0.123 times 5, divided by 8.85 times 10 to the negative 12, and then take the square roots of that last answer, and we are at 0.10 meters, or if you like, 10 centimeters. So this is a metal square, you know, about yay big or something, 10 centimeters by 10 centimeters. So there's my capacitor with a really thin half a millimeter spacing between them. So there's A. Going on to B, it says we now fill it with a dielectric and it stores more energy. And so let me say that this is the energy in B. They say what it is, but watch this for a moment. If I divide this by the energy that was stored back in A, this would be 1/2 times the capacitance that we had in B over the voltage squared. And this would be 1/2 times the capacitance we had in A over voltage squared. And it says all the things remain the same. So we're still hooked to the same power supply. So the 2,000 would cancel off, and we would get the capacitance at B over the capacitance of A. And then this, if you remember, was the capacitance lab one, where we said the capacitance now in B would be kappa times the parallel plate capacitor. And then the parallel capacitor in A was empty space, and so the empty space would cancel off. And so it might take a couple of thoughts to get there, but the dielectric constant is equal to the ratio of the energy stored, just like we did in the lab, where we said the dielectric constant was equal to the ratio of how the capacitance changed. So hopefully you recognize that and tied a little bit into the lab with you. But that would be this way of finding the dielectric constant, which would be answering this question, because it says here, if the capacitor is now filled with the dielectric and it stores this much energy, everything else staying the same, what material is used? And to identify the material, we have to know the material properties. You know, things like its conductivity, electrical conductivity. We don't know that, but we know its dielectric constant from the information given. If we wanted, to double check, we might check its electrical conductivity or its thermal conductivity. But given the information we have, we can only check its dielectric constant. And so the energy they said was 2.37 times 10 to the minus 3. And 3.54 times 10 to the minus 4. So if I grab my calculator here, actually, why don't I do this? I'll make this smaller and then this bigger, so I don't have to enter those into my calculator. So this would be 2.37 divided by 0.354, and I get a number of 6.69 for the dielectric constant. So what materials would have that dielectric constant? And of course, the hint here is to turn back to our chapter 26 and look at this table. And there's only one that's really close to that. And here it is, 6.7, neoprene rubber. So that's our material, neoprene rubber, kind of the standard rubber, the kind of synthetic stuff, I guess I should say, you know, waterproof boots, neoprene wetsuits come to mind, neoprene yoga pants come to mind. There's all kinds of neoprene rubber out there. One of your tarps. Anyways, but this is kind of your standard synthetic rubber. So rubber's a good answer there. This is the neoprene rubber. And so that must have been the material that we were placed in there, at least from the options we have in our chart. I'm sure there's other materials that have that dielectric constant, so we would have to, you know, have some other information to distinguish it from maybe some other materials that have the same dielectric constant. And that's why I said thermal conductivity or electrical conductivity, or even some of the material properties of elasticity, you know, something like that would tell us which one we're working with. Because I think there's quite a few rocks that have this dielectric constant. But once we said it had an elastic property, well, that would rule out all our rocks. Anyways, and then finally getting to the last one here, which says, now with this dielectric in place between the plates, what is the maximum voltage that can be applied to the capacitor before this dielectric breakdown? And so maybe just kind of a quick review here, but if you have this metal plate and below it you have another metal plate, and of course you make the top plate charge, also say positive, and the bottom one negative, you're going to get this huge electric field. And so if you put some material in here, in this case the neoprene rubber, okay, if that electric field gets to be too strong, it will tear the rubber molecules apart, and you'll have all kinds of problems. So there is an upper limit. And that's referred to as its strength, its dielectric strength. How strong is that material? And so scanning across to the rubber, we see we're at 12, and it's 12 million volts per meter. So what we're saying here is that the electric field must be less than or equal to 12 million volts per meter. And in our case, we've got a uniform electric field, so that's kind of the thing to remember for these parallel plates. So calculating the voltage, remember, is minus the integral of d dot ds, but that would just be electric field times distance if we're talking about a uniform field, and that's what we have here. So we can replace electric field, which is voltage over distance for this case. So this would be saying voltage over the separation distance must be less than our 12 million volts per meter. And so that means the voltage must be less than 12 million volts per meter times the separation, which is 0.0005 meters. So grabbing my calculator and putting in 12 million volts for 1 meter and 0.000 for the distance, 0.5, separating them, we're talking about keeping the voltage under 6,000 volts. You get this capacitor more than 6,000 volts and you'll rip this thing apart. And I might point out that would be laboratory settings. It's been my experience that, you know, in the real world, when you make these capacitors, we like to make them really fast, really cheap, and they're not pure material. And nobody's going to put the money into that. And so things will break apart long before 6,000. So the number actually on it is probably way down, probably half of that, at about 3,000. But nonetheless, in a perfect world, laboratory settings, perfect conditions, no moisture, everything's controlled, what we call laboratory conditions, you could get this capacitor up to 6,000 volts before there's problems. But in a more practical world, in a more, if this was a capacitor that's in your circuit board of your computer or something, 3,000 volts would be its maximum. All right, hey, we did it. We're done with the test, and hopefully this video is a little bit insightful for you, if whatever parts you needed and whatever parts you watched. Take care.